So today we solve rest of the question in specimen paper of CBSE board class 12 session 2025 and 26. So here we solve question number 21 part A. How does the impact parameter affect the trajectory of alpha particle scattered by a heavy nucleus? What is the value of impact parameter for here for head-on collision of alpha particle with the nucleus? So 21 part 1. The smaller the impact smaller the impact parameter mainly. Okay, parameter is larger is the angle of the alpha particle. Okay, is larger the angle at which alpha particles scatter. Okay. So larger the impact parameter, alpha particles less keeping in the original trajectory. Okay. So here that larger the impact parameter, alpha particle is less keeping its original trajectory. Trajectory. Okay. So here and what is the value of impact parameter? Value of impact parameter for head-on collision of alpha particle with the nucleus. So head-on the collision of the impact parameter is 0. Part here, another part that head-on collision, the impact parameter is 0. The impact parameter is 0. Okay. So next 21 to plot the graph of showing the variation of de Broglie wavelength lambda versus 1 by v, where v is the accelerating potential of a particle of mass m and charge q. Obtain the slope of this graph. So here if I plot a graph here, so now draw the lambda versus 1 by root v here. Okay, so that lambda equal to, from lambda equal to h by mu v from de Broglie hypothesis. Okay, and that is equal to h by the Planck's constant, that is root over of 2m qv. Okay, so here the slope, the main important is slope. This slope is look like this. This slope is look like a slope, and this slope, okay, that is equal to h by root over of 2mq. That's the slope. Okay, these are the slope here, and lambda square proportional to 1 over v, because it's or say that lambda proportional to root over of 1 by v. Okay, that's a straight line graph. Now jump to another question. That's the answer. Okay. Lambda square proportional to 1 by v, or you see that because there is a root here, obviously these are the slope. Okay, so that is lambda here. You see there is a root v here. Okay, so lambda square is 1 by v proportional to 1 by v, or lambda proportional to 1 by root v. Okay, both sides square. Take it. Now question number 22, with the help of circuit diagram explain the working of the full wave rectifier. Okay, so full wave rectifier circuit explanation here. So now there is a AC source and that center tap transformer, so that's a primary winding, and that's that secondary. Okay, so that is one diode D1, there is a diode is called D2, and okay, so there is center tap transformer, so there is a load R. Okay, now see that. So when diode look curves look like this, is AC source, okay, AC main source. When that's pulses here, now these pulses look like this. So when D1 is a forward bias, then D2 is the reverse bias because there is a negative here, and there is a PN junction. If P is falling negative, so if a PN, that's the P positive, N negative, that's the forward bias. When P is negative, P negative, N positive, so that's the reverse bias, so forward bias. Okay, so output graph is look like this. Okay, that's the input, and there see that. Okay, so here you see that when the positive cycle here, suppose there is a positive cycle, so D1 is the forward bias, so current passing to D1 and via load and grounded here. Okay, so output get a positive cycle. When D1 is a forward bias, so D2 is a reverse bias, and next cycle when there is a negative portion here, so negative portion means here, so D1 be the reverse bias, so now D2 be the forward bias. Now current passing to via D2 and goes to R. So now this negative portion revert in positive cycle, positive reaction, and similarly it goes on. Okay, so here D1 first is a D1 is a forward bias, D2 is a reverse bias. Here next cycle when D1 is a reverse bias, D2 here the forward bias. That's the full wave rectifier. Here we see that that's the full wave output here, rectifier. Okay, and now the next question. The current I1 in a wire getting divided into two wire with current I1, I2 and I3 at a junction in a circuit. And the current in the leaf of the wire are related to I1 equal to I2 plus I3. State the fundamental law from which that relation is derived. Explain the validation of law of conservation energy in Kirchhoff's voltage law. How the balancing condition get affected if they are interchanging the galvanometer and the cell in the Houston bridge. Okay, so that's the question number 22. Okay, question number 23 here. Okay, so here in part of A, 21 part A. Okay, so okay, the conservation of energy means very important. Okay, laws of conservation of electric charge. So first is the laws of conservation of electric charge. Okay, and the B, one part B, so KVL over the, obviously KVL over the conservation of electric charge. That's very important. The algebraic sum means here KVL say that algebraic sum of all potential drop in a closed loop be 0. That's the KVL explanation. Okay. Now that another question. How the balance condition get affected if the interchanging the galvanometer and the cell in the piston bridge. So here we see that no change in the balancing condition. So here no change in the balancing condition. Okay, is observed. Okay, there's a pH. Now question number 24. The fast moving a neutron collides with a nucleus of plutonium, thereby producing a xenon and a zirconium along with the neutron. Write the nuclear fission reaction. Find the energy released from about the nuclear fission reaction. These are the given data. That's a very important. And there's a mathematically. Okay. So here. Question number 24. Okay, so first of nuclear reaction here, the nuclear fission reaction. So fission reaction here, we see that the plutonium 239 mass number, the atomic number is 94 plus a neutron 10. Okay, and Xe is xenon 134 54 plus Zr, that is 103, but here is 40 plus 310. Okay, that's the first equation. And here the solving here, the given data obviously the delta mass. So obviously mass to put here. So delta m of plutonium plus mass, say that, suppose you say that not delta, suppose say the m for n10, the minus mass of Xe plus mass of Zr plus mass of obviously 3 times of mass of 10. So mass of plutonium is given. Okay, so that the data is a given. If there is a mass of plutonium is given, so you see that 239.052157 plus 1.00866 minus 133.905040 plus 102.9265 plus 3 into 1.00866. Okay, so finally if I added these two, we get 240.060817 minus, if I solve this with the help of a calculator obviously, 239.857617. So finally we get minus these two, we get 0.2032 AMU, atomic mass unit. So finally Q, that is equal to delta M, or say that M and energy 1U. Okay, that is delta M, we get 0.2032, and that is U energy, suppose 1 atomic 1U, that is equal to 931.5 mega electron volt. So finally get 931.5. So finally we get approximately 189, okay, mega electron volt. Need for one atomic mass unit. So 1 unit of mass energy is 931.5. So total with the total mass here, so multiplied by this, you get a omega electron. Okay. Now that next question, the question number 25. A compound microscope consists of an object lens. A focal length is 0.82 centimeter, and eyepiece of the length of focal length is 2.9 centimeter. An object is placed is 0.91 centimeter in front from the object lens. The image is formed at the near point is 25 centimeter from the eye. Calculate the angular magnification of the microscope. Draw the ray diagram of compound microscope in normal adjustment. Question number 25, part 1. 1 by V0 is equal to 1 by F0 minus 1 by U0. So here V0 is given. V0 is a 8.3 centimeter. So angular magnification. So angular magnification M, that is U0 by M0 d by Fe plus 1. That's the formula. So finally we get minus 8.3 by 0.91. All data is given obviously. Here 2.5 by 2.9 plus 1, and you solve this with the help of calculator. Okay, at minus 87.7. Okay, that's the angular magnification. Now draw the ray diagram of the compound microscope in normal adjustment. Okay, so 25 2. So here is normal adjustment means, suppose here is a lens, here is a bigger lens. Okay, there's the O, there's an E. Suppose there is an object here. Suppose here, choose a point here. Where is the F? This is that's F0. That's A, B. Okay, that's U0. And that length be the F0. Okay, so that's V0. And that's U E. Okay, and that's also that Fe. Now this ray passing to the focus, and this also parallel line meet at infinity. Parallel. Okay, so there is an eyepiece. Where key point here. Okay, that's a compound microscope diagram. 225 by 2. Part 2, compound microscope. Okay. Now the next question, question number 26. Draw the reflected wave in front of a plane wave in front of incident on a plane reflecting surface. Hence verify the laws of reflection using Huygens principles. Okay. 26. Okay, suppose there is a mirror. Okay, there are two rays. One, Okay, so back to the okay, and now the important part is that there's a normal, okay, I, R, okay, and there is a wave front here, so that's it. These are the perpendicular line. Okay, that's the angle with the 90. Here also be the perpendicular line. This angle also be the 90. Okay, so give the name A. There's a normal. There's a B. There's a C. That's name is D. That's name is normal. Okay, so if that angle I, so this angle also be the I. This angle also be the R. Okay, so total time taken from B to C travel, B to BC by velocity, okay, V. Suppose there is a speed of light, okay, and that's also the AD by same velocity V. So if V with the cancel, so we get a BC equal to UD. Remember that, that's a very important for deriving that's a reflection formula. Okay, BC equal to AD. Now there is a triangle here, triangle ABC, triangle ABC. So there is a sine I that is equal to BC by AC, and in triangle ADC sine R that is equal to obviously uh, perpendicular. Okay, that means AD by AC, hypotenuse here. AC is the hypotenuse in both cases. Okay, so we get BC from here, we get BC equal to AC sine I, and here we get AD equal to AC sine R. So BC equal to AD here. So BC equal to AC sine I, and AD equal to AC sine R. AC cancel, sine cancel, so I equal to R. Okay, there's the laws of reflection. The first laws of reflection. First laws of reflection. Okay, next is question number 27. Very high confidence. So if a point is size on an object having the charge 1 coulomb of mass 1 gram, object projected with a velocity of 2 I cap meter per second is from a point of 0 to centimeter 0. The region of the magnetic field is 0.1 k cap t, which spread in the first quadrant. Okay, so Q is given data here obviously. So there's a diagram. So obviously data are given here. So that's why question number 27. So Q equal to 1 coulomb, mass equal to 10 to the power minus 3 kg, velocity that is 2 meter per second, magnetic field B equal to minus 0.1 Tesla, K cap, magnetic field, vector field obviously. So the radius R we know that is equal to mb by qb. So here m equal to 10 to the power minus 3, and there is the v equal to 2 by q 1 coulomb, b is 0.1. Okay, Tesla here. So if I solve this, so point get 10, so 2 into 10 to the power minus 2 meter, so get 2 centimeter. So radius we get 2 centimeter. Okay, so if radius get R get 2 centimeter, if R gets 2 centimeter, this bending is look like this. As the radius R is 2 centimeter. 2 centimeter. Now that what will be the shape of the path following the given charge particle. There is a quarter circle. Okay, obviously there is a first, there's a circle. Okay, and what position will the cross the x-axis? So these x-axis, that's the 2 centimeter in the radius we find, and see what will be the kinetic energy of the particle when it enter the fourth quadrant. So that is as the work done by the B in a charged particle be the 0, so kinetic energy be the same. So kinetic energy K, that is equal to half m v square. M is 10 to the power minus 3, and get a v equal to velocity obviously given here, 2 meter per second. So that's get 4. So 2 cancel, 2 into 10 to the power minus 3 joule. So means 2 millijoule. That's a and C answer. Okay. Now the or option 27(2), if solenoid has a core of material with a relative permeability 200 and winding the solenoid are insulated from the core and carry current of 1 ampere if the number of turns is 2000 per meter. Okay, that's a great question. So mu r is given 200, okay, relative permeability, and I also given 1 ampere, and number of turns, okay, 2000 per meter. So okay, so that is 2000 per meter. Okay, so first how to solve a magnetic intensity. Magnetic intensity here, magnetic intensity. So formula H, that is equal to Ni. N, sorry. So we get H, Ni, N with the here 2000 and I with the 1 ampere. So we get 2 into 10 to the power 3. Okay, ampere per meter. Now the B, magnetic field. So B equal to mu 0 mu r times H. So mu 0 relative permeability of free space, that is 4 pi into 10 to the power minus 7. Here mu 0 is a 200 and H is given 2 into 10 to the power 3. So finally solve this, we get 20 10 to the power 5 into minus 2, obviously 2 to the 4 was 16 pi, that Tesla. Number C, magnetization, that M, that's the magnetization. Okay, that's the magnetization M, that is equal to mu r minus 1 times H. So finally we get mu r 200 minus 1, we get 199, and here is the H we get 2 into 10 to the power 3. So 398 into 10 to the power 3, okay, ampere per meter. So we solve 27 1 to 27 here. So next part we solve rest of the question. Okay. So today in the class here, if any doubt, always ask in comment section. I will try to give the answer. So we meet in next part. Okay. Thank you.